Okay.
Okay. All right. In 30 seconds, I'm going to start the live feed.
Okay. Just make sure you tell me that we're going, give me the cue that you are live. All right.
You got it. Prepare live stream. Going live.
Good evening, everyone. Welcome to Amateur Astronomers Incorporated, also known as AAI, for our weekly Fridays at Home presentations. AAI makes its home at William Miller Sperry Observatory on the campus of Union County College in Cranford, New Jersey. Since the observatory is closed at this time, we are holding our weekly presentations online. Our presenter this evening is Dr. Mary Lou West, who is a member of AAI. Mary Lou majored in math and physics at Cornell University and earned both a BA and MS in astrophysics and got her astrophysics PhD in Columbia University in New York City. She taught astronomy, physics, computer simulations, and methods of research at Montclair State University in Montclair, New Jersey for 42 years. She's now retired, has been a member of AAI for several years, and is our research committee chair at AAI. The title of her presentation is The Life of a Star and How We Figured It Out. So I'm going to turn this over to Mary Lou. Go ahead.
Hi, glad to be talking to you. I think the life of a star is really interesting, and it took us many decades to figure out how it actually worked. So the big question is, how does a star change as it gets older? We know that people and animals change as they get older. Partly their hair changes to lighter color. They get unsure of their steps. All sorts of things happen. But what do stars do? They don't walk and they don't have hair. So beginning questions, though, are such things as, well, what is a star? Are all the stars the same? And how long does the star age before it actually dies? What does that mean? Well, I thought I'd show you this picture here. So first of all, what is a star? Well, we all know it's a bright point of light up in the sky, and it makes its own light, which is an important criteria because a planet or a moon is not a star. It shines by reflected light. So for instance, we see the moon in the sky because it reflects the light of our sun. And if the sun went out, the moon would go out too. It'd be there, but we wouldn't see it. So it's not a star, does not make its own light. And then is our sun a star? Well, yes, it is. So looking at this picture here, this is a M17 by Tolga Gumosaiak, who's a member of AAI as well. And the question is, what could you get about a star from looking at a picture like this? Well, if we look at this one closely, we see several things right away. First of all, I think everybody should notice that the stars come in different brightnesses. There are some bright ones and there's some really faint ones and there's ones in the middle. Then also, if you look closely, they come in different colors. So there's some sort of yellowy orange ones, there's some sort of yellowy red ones, there's some blue ones, there's some white ones. So certainly they're not all the same color. And then something that's a little subtle on this one is that the stars are not all the same distance from each other. So you see that some of them are closer together and some of them are farther apart. And this particular picture was taken to highlight the group of stars in the middle, which is called a cluster of stars. But there's a lot more we could learn about stars than just this. So let's think about that. So the first easy ones, which we got just a moment ago, were brightness, color, and distance from each other. And those are easy to see. But there's a lot more things we can learn about stars. Many of them are difficult and sometimes tricky to try to figure out how we could get a judgment on them. So one of them is, as you see in the list here, distance from our solar system. The ancient people thought, well, all the stars are pasted on a large sphere, quite a distance from us, but they're all the same distance from the Earth. But that turns out not to be true. And it took us quite a while to figure out how to actually measure that. And it wasn't until the 1600s that we actually were able to measure the distance of any star from the Earth, and then to figure out that others were farther than that and get real numbers for them. So that's a difficult thing to do. Another thing is about the temperature. When we go into stores nowadays, we have somebody that measures the temperature of our forehead and says, yes, you may enter the store. But there's no way to point one of these temperature guns at a star and get any sort of relevant information. And it turns out that the color of the star is an indicator, a proxy for the temperature of the outside of the star, the outer layer of the star. We're going to talk about that in a bit, but that's difficult to do. Then there's the size, the diameter or the radius of a star. How big is it really? Are there stars that are bigger than others? And it turns out there are. And indeed, this is one of the major things that we learned about stars, is that some of them are quite a bit bigger than others, and some of them are really very, very tiny little things altogether. Last week, Al Gottlieb talked about some of the tiniest stars, the white dwarfs, and that was an interesting thing to learn about. Next comes mass. How much material is actually in that object? And that turns out to be exceedingly difficult. We know that for only a few stars, a few hundred stars actually, but not millions and millions like we know of all the other stuff. So that's a really tricky one, but that turns out to be absolutely essential. For a star, mass is its destiny. Whatever mass it has will determine how it will live and how it will die. Then another one is chemical composition. That takes spectroscopy, which is something I love to do. And I have several people at AI doing it with me, mostly Steve. And we can figure out the composition of a star by looking at very detailed spectroscopy of its colors. And it turns out that stars are 3/4 hydrogen, 1/4 helium, and 2% everything else. So it's really almost entirely hydrogen and helium, which is very unusual because there's very little of that on the Earth. So we're different here. Then we have companions. Do the stars have companions? Do they have other stars that are going around them? Do they have planets going around them? And we find that indeed there are lots of companions out there, and it's a very interesting thing to study now. AI has been busy in studying transits of exoplanets and trying to figure out their properties. And then, of course, the last one is the age, and that's what we're really up to today, to try to figure out the age of a star and how it changes as it does age, and that is very, very difficult. So that's a start. Here are some of the clues that we have. First of all, we find out that stars must age very slowly. They don't age to death in 70 or 100 years like people do, or 15 to 20 years like dogs do. We have historical records. People wrote down and did diagrams of stars 2,000, 3,000 years ago, even 4,000 years ago. And these stars are still there. So evidently, they don't age too much in 4,000 years. However, we have seen a few novae or supernovae, so that's Nova Stella, a new star. So there was no star over there before, and suddenly there's a star over there. And that tells us that some stars are born in some sense. And what could that be about? So if they're born, they must die. So, and then I have two diagrams here that are sort of the same and sort of not. And this is to show you that color tells the temperature of a star. So the one that's horizontal at the bottom that reads O, B, A, F, G, K, and M are pastel colors. There's very light lavender and sort of bluish and white and a little yellow and more yellow and orangey and kind of pink. And those are the real colors of stars. They're very delicate pastels. The vertical diagram, which says color and example and temperature, is an artist's drawing of colors. And this artist went overboard with the colors. So blue is blue. And it shouldn't be that way. It should be the delicate pastel colors. But nonetheless, I thought this was an interesting picture because it shows the names of particular stars that you can see with your eye in the sky. So Spica and Vega, and the sun, of course, is our yellow star up in the sky during the daytime. And then Arcturus and Antares are the red stars. And we see these at night. And something I have found over many years with star parties with families is that people my age have a trouble seeing colors, whereas little children, like 5-year-olds, can see the colors of stars right away. And it's wonderful if you have a 5-year-old in your group and you say, what color is that star over there? And they say, oh, that one's pink. You know, okay, good, now we know. Children are wonderful. Here's some more clues. Distance from the star to the solar system, to the Earth, is measured by a technique called parallax. And we can do this now because we have some good telescopes and satellites. And we can do this for millions of stars. It is quite a difficult thing, but we can actually do it. And once you get the parallax, you know how far it is from you to that star, and you know how bright the star appears to you, then you could back figure how bright the star really is and get its true brightness. Once you know the true brightness and you can see the temperature of the star from its color, then you can tell the diameter of the star, the size, because we know that the temperatures of the stars are all thousands of degrees, either Celsius or Fahrenheit. And that means that the star is made of a gas. There's nothing solid. There's nothing liquid. There's just a gas in a star. And this makes our job much easier because gases are very simple in their behavior. They're not nearly so complex as solids, where you could have like an Earth, which has layers within it and volcanoes which come up in liquids from deep layers. No, a star doesn't do that. It's just gas all the way through. So with a gas, we know for each square centimeter on its surface, at a given temperature, how much light it produces. So if we know the true brightness, the amount of light it produces, and the temperature, then we can tell the diameter. And so we come up with this figure here. And I think you can see that the sun, which they figure is this one in the upper middle of the diagram here, this yellow star, is a medium-sized star. Bigger than the star, or sorry, I lost my cursor. To the lower left of the star is a white dwarf star. That's the kind that Al was talking about last week. Even tinier is a neutron star, but there's not so many of those around. Then bigger than the star, they call the sun, is a giant star. And even bigger is a supergiant star. So in this diagram, they have not made the sizes as big as they might ought to. From the sun to a giant star, it's often 50 to 100 times diameter. And for a supergiant, even bigger than that. Some of them are truly, truly huge. So here's a little survey of the nearest stars to us. The circle of gray in the upper left says that within 30 light years of the solar system, there are 392 stars that have been counted. And of these 392 stars, they're arranged in lumps at the bottom as to what their characteristics are. So the ones marked A, that's the high temperature ones here. There would be 4 high temperature ones, and of the F stars, which are only slightly hotter than the sun, there's 1, 2, 3, 4, 5, 6, 7, 8 of them. And then of the G stars, which are the yellow ones, the same temperature as the sun, there's a whole bunch of those. A whole bunch of K stars, which are even cooler than the sun. And then we get to the M stars, and there's a ton of them. Look at all the M stars. So one thing we learned from this census is that most of the stars are not as bright and not as big as the sun. So even though we're kind of average, we're kind of a big average and kind of bigger than most of the other stars. Now this will give you a clue in this diagram to what we're eventually going to go for. And that is that if you look at the blue arrow that goes to the right here, it says the ones to the right are longer lived. Ah, and that's the age sort of thing that we're going to look for. Tell you more about that in a bit. So we have all these properties. Are any of these properties related to each other? Yes, they are. And the two main ones are the true brightness or luminosity of a star, and it's related to the temperature or the color. So they have this diagram on the right side. Luminosity, if you read on the right edge of it, goes from the bottom toward the top, getting brighter, brighter, brighter as you go up. Temperature is measured across the bottom of the diagram. It goes from the right to the left, which is kind of odd, but that's the way we've decided to do it historically. And so the cool stars are on the right, and it gets hotter, hotter, hotter as you go to the left, and the hottest ones are the blue-colored ones on the left side. This diagram was discovered by Hertzsprung and Russell, Ejnar Hertzsprung and Henry Russell, quite independently of each other during World War I. Hertzsprung was from Europe and Russell was from New Jersey. Hey! So Henry Norris Russell was our entree into world-class astronomy and into world-class science. He brought American science to the attention of the people in Europe and really changed the way they looked at these upstarts in the New World. It turns out that there are three groups, three groups of stars. The main sequence is the group of stars that goes diagonally from upper left to lower right. So that's across the diagram in the middle here. That's called the main sequence of stars. And it's called main because 90% of the stars in the sky fall somewhere along the sequence. So if you do a census and you plot them on this graph, there's where they are, 90% of them. And you say, okay, well, there must be another 10%. Where are they? Well, then there's the white dwarfs, which are down the lower left corner. These are here that Al talked about last week. These white dwarfs account for about 9%. So they're most of what remains of the stellar census. And then you have the 1%. And you go, oh, where are they? Oh, yes, they're in the upper right. These are the giants and the supergiants. These are the big stars. There aren't very many of them, only 1% of the stars, but they are beautiful and rare and gorgeous. And there they are. So the next big question is, okay, so we have some things we know about these stars. And the three types of stars are main sequence, white dwarf, and red giant. Are these three different types of stars, or are they perhaps three different stages in the life of the same type of star? Well, it could be either one. And as an example, I thought, suppose you went in the woods and you found a caterpillar. And you say, this caterpillar is long and skinny and it wiggles. Well, would it go with a worm and a snake, which also are long and skinny and wiggle? But actually they turn out to be different creatures, so no, it doesn't really go with them. Or does the caterpillar go with a cocoon and a butterfly, which don't look at all like it, but in fact do turn out to be different stages in the life of the same creature? So this is our conundrum to try to figure this out. Are there any questions at this point, George?
So far, no, Mary Lou.
Okay, on we go. Okay, so we have a mystery. We have three types of stars now that are fairly separate in their characteristics. How are they related to each other? And how could we figure this out? Well, in science, we use the scientific method. Yay, scientific method. This is the way we figure things out, and it has worked marvelously over many, many years and centuries. So the way it works is this: you observe something. So in fact, we have observed that there are three types of stars. Then you make some explanation or a theory or a hypothesis or an idea. You sometimes write down what you think is the relationship. And then you observe again to see if your explanation fits any new observations. Well, it probably doesn't completely. So then you change the explanation a little bit, hopefully only a little bit. And then you repeat this again. So you observe carefully, change the observation, change the explanation, observe again if it makes a prediction, make another adjustment, and do it again and again. And gradually you, by approximation, come into what is a really good idea of how these things fit together. So in the story of stars and how they age. Let's see how that works out. What is an explanation anyway? Well, explanation can be in words, it can be in mathematics, or it can be in physics. So in words, you want to say, well, this phenomenon depends on that phenomenon, or this phenomenon is caused by that one over there. Some sort of relationship, either just statistical or causal. Then we have a mathematical model. That's stronger generally, and it can be either qualitative or quantitative. Quantitative is better if you can do it. So in geometry, you could say something like, well, here we have a diagram in either 2 dimensions or 3 dimensions, and our various observations fit in this diagram somehow. And let's see, when this angle increases, then that angle over there increases too, or when this angle increases, that angle decreases. And then you could say when this angle increases by double, that one decreases by 10%. Get a little quantitative, that's really very cool. Or you make a graph, and the Hertzsprung-Russell diagram is a graph, one quantity plotted against another quantity. Then you could make a table of numeric values. If the brightness of the star is 1, 2, 3, 4, 5, 6, 7 in some unit, then the temperature comes out to be so many degrees, and see if that works. You hope eventually to get an equation. So you could say, you know, this quantity, the brightness is equal to the temperature to some power. It turns out it's pretty severe. It turns out, at least for brightness and temperature, that it's the 4th power. So the brightness of a star is related to the temperature of the star times itself, times itself, times itself again, 4 times. That's really a strong relationship. And then one could actually hope to do some physics, and that is to understand the mechanism by which this is related to that. So you want to say something, because of Newton's laws of motion, this force here causes that motion there. Or if you increase this property so much, then that property increases or decreases by so much. So this is what we're really aiming for, and there are many different goodnesses of theories for this. Okay, so let's look at some clues. So here's a clue. It says that distances of stars turn out to be very far away. So stars are very far from us, light years and light years. A light year is how far light can travel in a whole year, and it's very, very far. And then you look at the stars and you say, well, they're separate from each other on the photograph and very far from us, some of them quite different from us. So indeed, they're very isolated from each other. So I think this is a very significant thing to realize, that they are not at all close to each other. So in stars in our part of the universe are in general about 4 or 5 light years apart. So the nearest star to us is 4 light years from us, and it would take like 4 years to go from that star to us. So if we see the light from the star, it means it was still alive 4 years ago. That's good to know. But if the stars are isolated, then we find that they have a limited supply of energy. Whatever they have, they give off as light. They're shining light. Light is a kind of energy, so they're spending light like crazy. And because they're isolated, the energy cannot be resupplied. Uh-oh. When the energy is gone, they will stop shining, and then we will say they die. Because a star is that thing which shines. If they're not shining, we say it's dead. Okay? So the isolation, I think, is a very important thing. And at the end, we're going to come back to a special class that are not isolated, but not now. So we have energy sources in a star. If you want to think about energy sources, you want to think about, suppose you want to build an electric generating plant to supply the electricity for your lights and houses and things like that. What could you do? Well, you could have a combustion fossil fuel burning plant. In New Jersey, we had coal plants, we had oil burning plants. So you burn like a fire, and that requires some fuel, and you combine it with oxygen, and boom, it makes some energy, and you could, with a turbine, change it to electricity. Well, A star is made of 3/4 hydrogen. Good fuel, very nice fuel. However, it needs to combine with oxygen. Oxygen is only 1% of the mass in a star. Oh dear, you have a fuel but no oxidizer. That's not going to help much. Nope. So a star does not do any combustion. It just doesn't have the oxygen in it to carry that out. So the second type of energy for a power plant is gravitational energy. On Earth, that means you have a waterfall. You run the water over a fall. It falls in a gravitational field. And anything falling in a gravitational field gives you energy, and you can run a turbine with that. Okay. So on a star, there are no waterfalls, but the star itself, made of gas, can fall inwards. It can contract. It generally could do it very slowly, but it's falling inwards, and that can produce energy. And then the third type is nuclear fusion. You could have a nuclear power plant. In stars, the nuclear power plant would be fusion. And in that, small nuclei combine to become heavier nuclei. So hydrogen, which is most of the star, is the smallest of the nuclei. So that's perfect. You start with the smallest one and build up from there. That's a great fuel to have. So now let's talk about the bottom two here, gravitational and nuclear. If you had the total amount of energy that you could get from either of these, so gravitational energy, the total would be, you start with a star at whatever size it is, and you contract it down to a wee tiny little point. How much energy is that? Okay. I'm going to represent that as a dime. See the dime? Okay. Then we have nuclear fusion. Nuclear fusion is when the small nuclei, like hydrogen, combine to make larger nuclei. And we know how much energy that gives because we've done that. And we could figure if the whole of the star became nuclear fusion, how much would it have? How many dimes could you get from that? Well, what you get is one of these. So the amount of energy available from gravity is very small compared to the amount of energy you get from fusion. So if you were a star and you had these two sources of energy, went shopping, oh man, you want to spend this one. You got lots of possibilities here. You don't want to spend this one because it's like nothing, almost like nothing. However, there are times when this doesn't work at all. You cannot put this in a parking meter. You could put this in a parking meter. So at that point, if you're stuck with you only can have coins, this is all you got, and that's what you got to use. So the star does that. It toggles back and forth between this one and that one, and this one and that one, and only does gravity when it absolutely has to and cannot get to the fusion. Let's think about that more. Well, we want to make a model of the life of a star so it can age. So first we make a model of what it starts with. So a numerical model, we start with a huge cloud of cold gas and dust from the beginning of the universe. Here's a picture of one of those. So the Eagle Nebula. It's made of hydrogen, helium, and oxygen is the third element. So it's 73%, 25%, 1%, and then all else, the whole rest of the periodic table is only 1% all put together, which is really pretty tiny. And so the tiny stuff like carbon and iron and gold and diamonds is very small percent, but it's there. That's good to know. So anyway, we have this cloud. It has to get jostled somehow, and it begins then to fall in, which means it decreases in its diameter and falls in because it is attracted by the gravity of all the other little bits in the cloud. Once it starts to fall in, this releases gravitational energy. That contraction causes an increase in pressure because you take material and put it in a smaller volume, it increases in pressure, and also an increase in temperature. Aha! Once the cloud begins to increase in temperature, it's on its way to living and eventually dying. So for a model of stellar structure, you need several equations. This is the physics that goes into making a model of a star. You need Newton's law of gravity, the mass of individual bits and how far they are from each other, tells you the force of gravity at any point. Generally, what we do is we divide a star up into rings, like an onion, and for each ring, we decide calculate how much the gravity force is. Then we need the ideal gas law. Temperature, pressure, and density are related for a gas at high temperatures. Then we get to talk about the emission of light from a hot gas. A hot gas is a black body. The temperature determines how much light comes off and what colors it is. The opacity of the gas, though, is an interesting little tidbit. Right toward the edge of a star, the temperatures are lesser than they are in the very middle of the star where it's hottest. And so the opacity can at that point change drastically when the gas goes from being ionized to becoming an atom. And when it's an atom, it has a different opacity than when it's dissociated. So that's a very interesting bit there. Heat transport. There are three methods of transporting heat from this place to that place. I'm sure you all learned this in 7th grade or something like that. Conduction, convection, and radiation. So conduction takes a solid object or a liquid object, so that's out because there's none of that in the star. So we have radiation and convection. Convection is when they have big gas motions, like the boiling of spaghetti sauce. And nuclear fusion, which provides the main source of energy, depends on the composition, the temperature, the density, and you can figure out the energy there. But I want to tell you something about nuclear power. So I have another thing here, and I want you to listen and think what this could possibly be. Everybody see that? It's Velcro. Wonderful stuff. So Velcro has some properties like nuclear fusion. It has a very small contact distance, different from gravity. So with gravity, if you hold something up and the gravity of the Earth is way down there, the gravity of the Earth can figure out how to pull it down even over thousands of miles. But with Velcro, the only time Velcro can hold something up is that if it actually touches it, and then it holds it up. And if you just almost touch it, but not quite, it falls down. So Velcro is very strong. It can certainly hold something up against gravity. It's stronger than gravity, but only if the other material is within 1/8 of an inch of it. Otherwise, it doesn't feel it at all. So it has a very strange force equation. It's all or nothing, basically. And nuclear fusion is like that in a star. So in a model, you assume spherical symmetry. You assume that the star is not rotating. That makes it spherically symmetric. And you assume it's quasi-static in time, which means you take time steps that are slow enough, quick enough, that nothing really changes much in any individual time period. And you just work along and you subtract energy, which is radiated away every year from your model until something changes, and suddenly something will. So here's a diagram I thought was pretty an artist's idea of heat transfer. So we have, as you see, convection or radiation. And in stars of different masses, it's different. So in the star of large mass, that's the blue one on the left, larger than 1.5 solar masses, it has convection in the center and then radiation in the outer layers. In the middle one, the yellow one, it's 0.5 to 1.5 solar masses, so this includes the sun. It's radiation zone in the middle and convection toward the outside. And then to the right, we have the less than 0.5 solar masses, the smaller stars, and they have convection entirely and no radiation zone at all. So where it changes the method of heat transport will change the model. So some consequences. Well, hotter temperatures, if the star is hotter at any point, it will radiate away more light and it will be bright, brighter than a cooler star. Really high temperatures and pressures in the core will start the nuclear fusion reaction. So this fusion reaction has to take tremendous pressure to get the nuclei close enough to each other to cross that tiny gap and then get stuck to each other. And once they're stuck really well. And they release a tremendous amount of energy. The reaction is that hydrogen nuclei, a hydrogen nucleus is called a proton, becomes a helium nucleus. So you have 1 plus 2 plus 3 plus 4, and you get rid of some positrons, and you have a helium nucleus. So when people sometimes talk about, well, the hydrogen burns to helium, or the hydrogen burns, and you think, oh my God, it's burning and nothing is left. No, what's left is pretty much the same amount of material, but it's just called helium. So it's not that the center of the star goes empty, it just becomes full of ashes. Well, once nuclear fusion begins, it stops the infall. The diameter stays the same. Nuclear fusion is completely capable of stopping any gravitational energy from being released at all. So that's the $20 bill. This one can keep it from infalling for a long time. The models say it takes 90% of the star's total lifetime before it releases its grip at all. And that's the main sequence of stars. Ha-ha! Yay! The model agrees with the observations we have already found on the Hertzsprung-Russell diagram, or HR diagram if you can't spell it. Next question. What ends the main sequence stage? What stage comes next? Will it become a white dwarf or a red giant, or what? So now we have to look at the model more carefully and see exactly what happens toward the end of the main sequence stage. Well, the model predicts the change will be that the star's core, which is about 10% or 15% of the diameter, so just way little bit of stuff in the middle, will run out of hydrogen and become all helium. Then the nuclear reaction dwindles away. Then the star contracts gravitationally again, having not much fusion left. It goes back to gravity. It's the only thing it's got to spend. Once you start gravity, things contract, the temperature shoots up. Then nuclear fusion can begin in the shell of material around the previous core. So you got ashes of helium and then a shell burning hydrogen. Well, this is a stable situation once again, but the shell is skinny, so it doesn't last very long really, but it's closer to the outside of the star and it just poof, puffs off the outer layer of the star. And from the outside, we see the puffed out layer and we say, oh, look, this is a red giant star. So red giant is the answer to what comes next. Unfortunately, red giants are often pretty big, and so the puffed up layer would go out and it would burn up the inner planets. So Mercury, Venus, Earth would be burned up. By this time we better move. Yes. But we observe there are red giant stars and they have the right properties that the model does predict. So yay, the model works again. We do believe that these models are working properly. How about the next model prediction? Well, the core nuclear fusion begins again once the shell begins to dwindle a little bit. And now we have a new fuel. Helium can in fact become a fuel, and it can combine to form carbon nuclei. And carbon can eventually make oxygen. So the star will become a main sequence star. Again, main sequence turns out to mean doing nuclear fusion in the core. But this time it's a hotter star than the first time around. So it's leftwards on the main sequence, further up, further to the left in the Hertzsprung-Russell diagram. And then it will become a red giant for the second time also. So in this diagram here, we can see that the star is on the main sequence. They have a line starting at the sun now, going off to the upper right, where it becomes a red giant, and then doubling back toward the main sequence again, and then going back to being a red giant again. So it kind of look like a bird's beak there. That's called the horizontal branch of the giants. And we observe carefully, and yes, there are some stars there. There are some stars making a horizontal branch from the giants on the Hertzsprung-Russell diagram. So we interpret that to mean that they're in the second go round of main sequence red giant that the models do in fact predict. So the models seem to have got this right. It took many years of graduate students to get these models to work right, just saying. Then we have another clue. The model predicts that the transition from main sequence to red giant will happen quicker for stars of larger mass. Well, where are the larger mass stars? On the main sequence, they are the stars at the hotter end of the main sequence, which is the leftwards part, the upper left part of the main sequence. So if you had a litter of stars that had stars of different masses, then the bigger massive ones would age quicker and they would go whooping off to be red giants before anybody else. We could do that. We can observe a globular cluster of stars. Here's a picture of one right here. Those stars were all born at the same time. And there's 1/3 of a million, 500,000 stars in that picture. Some of them are little, some of them are medium-sized mass, and some of them are large mass. We can measure their temperatures, we can measure their brightnesses, we can plot them on the Hertzsprung-Russell diagram, and we find that if we have looked at several different of these globular clusters, and there's like 100 of them, then we find that when the top of the main sequence is dwindling away, the number of red giant stars increases in that cluster. Yay, the model works again. Okay. And it works in many clusters. So here's a composite diagram in which we have a Hertzsprung-Russell diagram. So the bottom is temperature increasing to the left. Vertical axis is absolute brightness, luminosity going upwards to the top. And here's a whole bunch of different clusters. So NGC 2362 is near the top. It's hardly begun to age at all. H and Chi Persei below it have aged. Then we have some others down there. We have the Pleiades, M41, M11, NGC 752, M67, NGC 188, as you go down to different ages. So the ones that have peeled off the main sequence further down are the oldest ones. So of this particular sample, it would say that NGC 188 is the oldest cluster in this group, and H and Chi Persei is one of the younger clusters. And you see that these paths on this diagram are not straight lines, they're wiggly, and they go up and wiggle and up. And there's an interesting one, M3, which cuts across a lot of the others. So this one is a puzzle. We have to look more carefully at M3, it's the red one. Why is it different from all the other ones? Also, there's a Hertzsprung gap, that yellow part in the middle. There are very, very few stars in between where that gap is. So we interpret that to mean, it must mean that the stars which are in that combination of temperature and brightness change rather rapidly and go whooping off and become a red giant very quickly. So we shall see. Okay. So then there's the final stage. After the helium fuel is totally used up, so first in the core and then in the shell around the core, then the star, like the sun, has no more fuel. It cannot get to the temperature needed to make carbon fusion or oxygen fusion happen. And the star then throws off the whole outer layer, and it's called a planetary nebula. They are just beautiful to see through a telescope or to see in a book of pictures. So here's one here called the Helix Nebula. And then in the very middle, you can see the core of the star that remains, the part that's done the fusion, and it's called a white dwarf star. So in this picture, I don't know if you could see it. It's right there. Can you see my cursor? That little blip in the middle is the white dwarf star, which is the core, and it had all that other stuff around it originally, and now it's shed its skin, and it will just shed its energy and eventually die. It's supported against its own gravity by electron degeneracy pressure, which is a very quantum mechanical sort of thing. Very interesting if you'd like to follow up on that, but not to be discussed today. And it maintains a stable, tiny diameter forever. It'll be about the size of the Earth. It's only a few thousand kilometers across rather than 1,000,000 kilometers. And it cools very, very gently. It has a hard time shedding energy. That's why it's so faint. But it will shed its energy over a long period of time. We will see it there for a long time. And meanwhile, the nebula will go away. We observe white dwarf stars in the sky, and they have the right temperature, and they have the right luminosity. Yay, the model works again. Good job. I thought I'd show you some more pictures of these planetary nebulae or death nebulae. They were originally thought to resemble planets, but they are not planets. That was just having an old little telescope. Big telescope shows marvelous details. Look at these beautiful things. So there's the dumbbell and the ring. And in some of these, many of these, you can see the white dwarf right in the middle, the core of a dying star. So the one on the left was taken by Mike Selby and Tolga Gumasiak in 2017. The right one was taken by a group of people and at NASA, so it's NASA Heritage, and it was an APOD, an astronomy picture of the day in 2018. Here's one I think I always like. This is called the Cat's Eye Nebula. And usually you look at the picture at the right. Usually you see just the inner part, the elongated part, and it does kind of look like a cat's eye. And then if you see the whole thing, you print the rest of it, the golden halo on the outside is very faint and it's been hyped up so you could see it here. And so it does look kind of furry like a cat too. This was taken by the Nordic Optical Telescope Group on the Canary Islands, and they got an APOD in 2014 for this picture. I was talking about this to one of my friends, Sam, and he drew a picture of it. So the lower left here, we have Sam's interpretation without seeing the picture of what a cat's eye nebula would look like. And I think you can see that he has on the right side, this roundy thing is the cat's eye, and then the black around it is empty space. Go, Sam. Sam is 5. So another consequence. What happens to the gas in the death nebulae? Well, the gas expands out into space. Sometimes it joins a cold cloud of gas and dust somewhere nearby. Maybe it will form a new star. Maybe that star system would have planets. We think that at least half the stars do have planets. And those planets then would have more helium, more carbon, and more oxygen than the previous generation of star systems had, because they have the remains of a star that did the processing. Those are interesting elements. Well, not helium, but carbon and oxygen. Hey. And we are stardust. We indeed, the carbon in our bodies came from the outer layers of a long ago red giant star. So pat your cheek and say, yay, red giant star. I'm glad you died for me. So here's a summary of the life cycle of a star. Starts on the left, you have the cloud, and then for a long time, it's just a simple yellow ball, and then eventually warms up enough to become a red giant. Makes a death nebulae, a planetary nebulae, does this twice, and then becomes a white dwarf star. Thought that was a nice diagram. Here's another summary of the life of a star. You have a cold cloud or nebula, becomes a main sequence star, then a red giant star, repeats the main sequence in red giant, becomes a white dwarf and a planetary nebula dust cloud. And this one says, this diagram, that the upper line here is the average star like the sun, and the lower line is a massive star. And the difference here is it becomes a supergiant star, red supergiant, and then a supernova explosion, which could leave the core as a neutron star or a black hole. Ooh, something to think about for another talk. And then there's more predictions. So here's one of the things I think that's intriguing. Variability is part of a star's life. Most of them go through a period of variability. And at what temperature and brightness does this happen? Well, the models can predict this, and often depends on the opacity as it changes like a switch. There are instability strips on the Hertzsprung-Russell diagram, and we can look at such a diagram. So here's one from a particular group of people, and I've colored in pink the instability strip for the Cepheid variables. And you can see there a certain temperature and brightness. It's a little bit tilted. But if you look at one of the paths of stellar evolution, the star goes off to the right, goes through that strip, boop, 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 a couple times, becomes a red giant, then goes and does the replay of main sequence and red giant. The top 3 of these pass cross over the strip again. The bottom one does not cross over the strip again. So that says something about the population statistics that you could expect from these models as to how many stars are in the population in the Cepheid strip. The period of variability is different as you go along the strip. And the rate of change of the period, is it speeding up or slowing down, can tell you whether the star is going to the left or to the right through the strip. And that's going to be our next part of understanding this. So more interesting bits of predictions from these models. First of all, we should talk briefly that there are binary stars in the universe. Many of them, very common, 50, 70, 80% of the stars are in binary systems. Mostly they're like the top diagram here. They have the stars in blue. And the black line, the 2 sort of teardrop things, are the Roche zone of the star. So that's within that, the star controls its own gravity. And outside of that, the gravity of the other star has an influence. Some stars, however, become semi-detached, which is the bottom diagram. So the star on the left here has filled its Roche zone. And when it gets to that point of crossover, it can then shed mass through that point onto the other star. So gas will begin to flow from the donor star to the acceptor star. And mass will flow for quite a while from the left-hand to the right-hand star in this. This will change the aging of both the stars. This is where they can be resupplied, at least one of them. Sometimes the ones that are resupplied are rejuvenated and they're called blue stragglers. If the acceptor star is already a white dwarf and it gets enough resupply, it can go to become a supernova explosion. And that's very dramatic. So that's the summary. A star's life is pretty interesting. And I think it took us an interesting series of models to figure it out. Thank you for your attention. Are there any questions?
Mary Lou, there's one question in the Q&A, but I have one myself that I'd like to ask
Sure,
you.
go for it.
Okay. When it comes to binary stars, help me imagine, I guess, the distance between them. Are they close? Are they like as far as like say Pluto would be from our star? Like, are they even farther than that? And like the scale is like hard to imagine because when we see a binary, like what do we look like? Help me imagine the scale when it comes to a binary star.
Okay, binary stars come in all sorts of different separations. Most of them are like somewhat bigger than the solar system. So if the sun were one of them, the other one would be 2, 3, 4 times the distance of Pluto. And so they go around, they'll never touch each other. They're quite separate, but they are stuck in going around their common center of mass. However, there are some of them that are born almost like Siamese twins that are born fairly close to each other. Some that are born like the sun and where Jupiter is. So they're separate for a while, but when one of them becomes a red giant, boy, it spills over into the other Roche zone and just spills gas onto the other one. That messes up both of them. But we think the ones that are that close are pretty rare. When they are found, they're studied carefully to see what particular things they could tell us about the life of a star in general. But most of them are quite separate. So, light weeks apart, that sort of thing, beyond Pluto.
Got it.
Yeah.
Okay, so we do have a series of questions streaming in now. The first one comes from Nancy Toscas. I'm assuming not the sun, but she's asking what is the nearest star to us?
So the nearest star, this is a trick question. If you're ever on a quiz show and they say, what is the nearest star to us? You have to blurt out in one breath, it is the sun, but also Alpha Centauri. Because if you say the sun, they said, oh, no, I meant Alpha Centauri. And if you say Alpha Centauri, they said, no, it's the sun, silly. So the nearest star to us is Alpha Centauri, but actually that turns out to be Alpha Centauri A, B, and C, 3 stars going around each other. So 2 in a close binary and another further out. And that one is called Proxima, which means nearest one. So Proxima Centauri is the closest star to us. And That's 4 light years away. Long, too long to go to, even that one.
Got it. All right. So Dr. Al Gottlieb states, mentioned that binary stars help us find the mass of the stars. Just a
Okay,
comment.
so the mass of a star turns out to be its major property. If you know the mass of a star, then you can figure where it is going to be on the main sequence, and then where it's going to be as a red giant, and then how many times it's going to go back and forth doing the replays. So the mass is a very important thing. And we wish they had a big scale. You put a scale out there and put the star on it and measure it. The only way we figure out to get a reliable measure of mass is to figure out what its mass affects. And so the best thing to do there is if you have a binary star, two of them going around each other, then the mass of one affects the other, and the mass of the other affects the one. And it's pretty easy to get from the period and the separation, period of time and the separation, the mass of the two of them together. And then it's a little tricky, but you need spectroscopy to get the mass of each of them individually. But we can do that for 100, 200, 300 pairs. And it turns out that the mass does correlate really well with their position on the main sequence, and so that's a very useful thing. But yeah, you have to find what it is that it affects, and that's another star.
Excellent. All right. So we have one question. It's stated as from an anonymous attendee. In the news about a year ago, there was a report of a star that, when aged, seemed to be older than the universe. This seems impossible.
Yes, it
Have,
is impossible.
have astronomers solved this mystery yet? I think it was named the Methuselah star.
The Methuselah star. Yes. So one thing that they reported in the article but didn't report was the age, and what they didn't report was the error bars on it. So the age of the universe is 13.7 or 8 billion years, and the star's age turned out to be 13.7 or 13.6 plus or minus 0.3. You know, it was very nearly the age of the universe, and had a big error bar. So when that was measured better, they said, oh yeah, it's just a tad less than the age of the universe, because no, you can't have that, despite all bad jokes.
Excellent. All
Yeah.
right. So you have a question from Brian Lemley. How do
Okay.
red dwarfs evolve?
Say again.
How do red dwarfs evolve?
Okay. Red dwarfs is a name that we give to the stars on the far lower right part of the main sequence. There was confusion years ago about the red stars, and before we actually measured them really well. And so then finally people said, oh, there's these red ones that are giants, and what other red ones are left we'll call dwarfs. So the red dwarfs are the ones on the main sequence. They're not all that small. And mostly they have not evolved at all since the beginning of the universe, or since they were formed, however long ago that might be. They're still chugging along, doing the hydrogen to helium nuclear fusion in their core, slowly. And we would expect them to age not in 10 billion years like the sun, but maybe more like 100 billion years. They're going to last a long time. So if we ever run out of stars to go to, we should go to one of them and just snuggle up close to it and keep warm. It's not a big fire, but it's going to burn for a long time. Yep.
Great. All right. Well, our anonymous attendee commented, great answer. Thank you. We have two more.
Okay.
We have two more questions. One
Sure.
is from Mary Lou. No, excuse me. One is from Mary Duca.
Oh, another Mary.
Mary Lou, could our Earth survive in a binary star system?
Ooh, that's a good question. Maybe. It was thought originally, or it was thought 20 years ago, that a planet in a binary system was in grave danger and would either be ejected or eaten by one of the stars. And then we have found recently with exoplanets that there's a good handful, I don't know, 10, 20 of stars in binary systems that have a planet or two. And so there's some tight constraints. The star has to be fairly close to its main star that it's going around. The planet has to be close to its main star it's going around and not wander too far away from it so it gets caught by the other star. So it can't be just anywhere, as could be in our solar system, but there's a kind of a ring around the main star. And also you want, so there's that situation. Or you want the two stars themselves to be close together as if they were a single star, and then the planet could be way out here going around the pair of them. So that's another possibility. But stars like that would have, planets like that would have a rough life. I don't know if they could ever have, you know, chemical life on them, biological life, because mostly they would get such a changing day, night, life cycle, hot, cold. I don't know. Good question.
Right. Thank you. Yeah. Okay. A question from Jeff Glazer. Is a certain star type more likely to have a planetary system?
That's a great question. I just heard the answer last week. So yes, Jack, it is true. We've got now about 4,000 exoplanets known. We know where they are, we know what star they're going around, how many of them are going around that particular star. So we have now a sample which is considered statistically significant. So what people have been doing is trying to look at each of these individual host stars and get its properties really, really well. Get the error bars down on its mass, its temperature, its everything. And then figure how this affects the planets and the number of planets. And so I heard a talk last week in which somebody has done this and found that indeed the statistics are such that most planets are going around the cool stars, the cool red stars, the cool orange stars on the main sequence. And as you go up to hotter temperatures, you get fewer stars, fewer planets per star, and also fewer total mass of planets. So by the time you get to the white stars like Vega, very few, maybe it only has one planet, or if it has two, they're small. Whereas if you go to an M star on the main sequence, it could have 6 or 8 planets. It has a real litter. So good question. Yes, statistics can get you all sorts of good stuff.
One last question from Nancy Twaskas. Were the red giants and white dwarfs once on the main sequence?
Yes, they were. So any star that's a red giant or a white dwarf was once on the main sequence. So it's like looking in a population of people, and if you see a person with white hair and a cane and thick eyeglasses, they were probably once a baby, for sure. And if you see somebody that's a teenager and has got long wild hair and is playing wild music, they were also a baby. You can really nail that down. They were, and they don't believe it, but they were.
Great. You got a LOL from Nancy with the follow-up of good answers. They're both old.
Yeah. Right. So something else I heard that I thought was very interesting a couple of weeks ago was that around stars on the main sequence, there are planets, and there's a habitable zone where the temperature is such that it's cool enough that you form liquid water and not so cool that you form ice. And in that zone, you could have planets. And they could be there for a long time, and that's where we are, it's the Earth, around our sun. And we have chemical, biological life. Cool, that's great. Is there any other time in a star's life when it could have a habitable zone? Well, that would really work. Red giants, no, they're just too quick about it. They flash in a pan in biological terms, so they're no good for actually building life. But then you have white dwarfs, and you think, well, white dwarfs cool really, really slowly, so they have a habitable zone. Maybe they could have planets there. Oh no, they would have burned them up when they were a red giant until 3 weeks ago when they found a couple. So there's at least one star going around a white dwarf in its habitable zone. We have a second chance. Now, how it got there, nobody knows. But intriguing.
Nancy did add some clarifications. She said white dwarves and red giants are both old. Not they
Yes.
are both old.
Yes, they are. They're both old.
And then she also says main sequence are babies and teenagers.
Yes.
Okay. Thank you, Nancy. All right.
Yeah.
That's it for the questions.
Well, thank you very much. The great questions. I'm glad people could think and ask these questions. Thank you.
Great. I'll turn it to you and stop the stream, Mary.
Well, thank you, Mary Lou. That was really very interesting and very informative. I just want to remind everybody you can join us every Friday night at 8 p.m. online. And I want to mention that our presenter next Friday, July 24th, is Dr. Jeremy Carlo. And the title of his presentation is The Big Bang and the Laws of Physics. So thank you for joining us and wishing everyone clear skies.